Okay, so the last concept that we went through that's going to be on the exam was groundwater. And so if we look at all the water on the planet's surface, the vast majority of it is in salt water present in the oceans. A little bit of it is present as permanent ice on Antarctica and Greenland primarily. And about 0.6% of that water is present as groundwater. Extremely small amount of it is present as lakes and rivers. Um, if we just kind of describe what we see, groundwater flow rates are really slow, centimeters per day or meters per year. It depends on the material through which it's flowing, but groundwater can stay in a reservoir for thousands of years. Um, in the immediate subsurface, you have an unsaturated zone where pore spaces are partially filled with air, and that air exists at atmospheric pressure. Um, Beneath that, though, if you keep going downward, eventually you're going to hit the saturated zone, beneath which pore spaces are filled with fluids. The boundary between those two areas is called the water table. So if you dig down or drill down, eventually you'll hit the water table, and below that there will be groundwater. Okay, and so it looks something like this, right? And that groundwater is going to be present in some type of a void space in the rock, right? Most commonly, that's going to be pore space in between grains of sediment, or it's going to be some kind of connected network of fractures. The pore space refers to, excuse me, refers to that void, that open space in between grains of sediment. That's colored blue there. But how connected those pores are is really important to the flow of groundwater. And so that's a concept that we call permeability, or a property that we call permeability. So you can measure the pore space of a rock, and you can also measure the permeability. It's kind of the resistance to flow. All right, so this is a sandstone, an Ordovician age sandstone. It's got a ton of pore space, and those pores are relatively well connected, right? And so it would have a pretty high permeability as well as a pretty high porosity. Something like a vesicular basalt here, it has a lot of these vesicles, which are open space. They are pore space, but they're not connected. So it's high porosity, low permeability. Okay, but in any case, aquifers are going to be, water is going to be is going to exist within those pore spaces, wherever that may be, beneath the water table in the saturated zone. Right, you can drill into that and pump water out. If you do that, it will cause the water table to go down, these cones of depression, and over time that can lead to problems. You can run out of water, have to drill a deeper well. Eventually, you might hit salt water down there. Can also lead to a lot of subsidence as the ground compacts when you take that water out. That can be problematic. But in general, water tables can be kind of shallow and permeable, and you have this unsaturated zone above. Those reservoirs are not under pressure, not under any more pressure than is being exerted by this water right here. You can also have a confined aquifer, though, like this, where there are impermeable confining layers above and below, like it says there. And the zone of recharge is up here in the mountains at this level. And because of that, there's hydraulic pressure pushing down with enough force to push water back up to that level, if that makes sense. And so if you drilled a well right here, you would need to pump water out of this confined aquifer. But if you drill a well down here, because it's below that surface there, it's gonna water will just flow out of it. It's called an artesian well. And these exist actually in Claremont because of the way the water table exists in these faults, which actually cause the water table to be higher on the San Antonio or the San Gabriel side of the faults than on the valley side. And so that can cause a situation like this where you have springs, and that's exactly what's happening in Claremont with these cienagas that we talked about in the campus walking tour. Talks a lot about those. So it's kind of like this, where the water comes out. This is something called a perch water table. That's in the shallow zone where you have an unsaturated zone above, but Claremont is more of a situation like this. The other topics we talked about, excuse me, talking about groundwater were possible saltwater intrusion. And so it's possible to have an island like this, or at the coast this happens, where you have fresh water beneath the land, but then there's salt water on the outsides. And so you have a saltwater, the groundwater is salty like that, but there's some lens of fresh water in between. You can run into problems if you pump too much in an area like that. We talked specifically about New York, Manhattan, where they re-inject highly treated wastewater into the groundwater reservoir to keep the salt water back. In any case, groundwater is it takes a long time to flow. Like I said, it's recharged by rain primarily. We have engineered systems to recharge groundwater reservoirs, but in general, naturally, it's recharged by rain, and there's some amount of discharge. A lot of it is, naturally would be springs, but we tap into this and use it for a variety of purposes. You could talk about a whole bunch of different case studies with respect to this. A lot of them would deal with subsidence, though, where cities or agricultural regions have sunk because they've pumped out enough groundwater to allow those pore spaces to collapse. Let's see. That's essentially what this figure was referring to. But yeah, that mostly sums up the discussion about groundwater. In terms of California, we get a lot of water out of groundwater reservoirs. There are hundreds of individual groundwater reservoirs across the state. We get a lot of our water from that. We also trap a lot of surface water in reservoirs, and we get a lot of water from the Colorado River as well. But we pump a lot of water out. That was sort of the message of this very last slide here, that a lot of groundwater reservoirs are going down. This is cumulative groundwater loss. In any case, that more or less sums it up. So I'll cut it off there. Thanks.